Imagine a cold, moonless night, where silence is broken only by distant calls. You're about to step off the curb when suddenly, a car approaches, headlights piercing the fog. In that split second, destiny intervenes. The stranger's life is lost, but yours is saved, and in your pocket you find a mysterious note: "Study physics." Decades later, you unlock the secrets of time travel. The first ever functioning time machine hums before you. But what if that note, the one that changed your life, holds the key to the universe's deepest mysteries? Join us as we explore the possibility: is time travel possible within our universe? And what if the answers are closer than you think? The paradoxes of time travel. Stepping into your machine, you set the controls to revisit that fateful night. The goal? To save your younger self from the oncoming car. It seems straightforward, an act of heroism that would alter history. But beneath this seemingly simple plan lie profound questions and paradoxes that challenge our understanding of reality. The Bootstrap Paradox. When you travel back in time and hand the note to your teenage self, who is its true author? The note appears to exist in a temporal loop, with no origin, an idea known as the Bootstrap Paradox. It's a causal loop where the cause and effect feed back into each other endlessly, creating a piece of information that has no clear point of origin. The note, in essence, exists because you have it. You have it because it exists, an uncaused cause. The Predestination Paradox. Suppose your older self saves your younger self, who then grows up to do the same, creating an infinite chain of time loops. Does this cycle ever break? Does the note grow more tattered with each iteration, or does it remain pristine? The Predestination Paradox questions whether these loops are eternal, or if they eventually fade or resolve. The Ex Nihilo Paradox. Another question emerges: where did the idea of studying physics originate? Did it just appear out of nowhere, a concept with no clear beginning? This is the Ex Nihilo Paradox, challenging our notions of causality and origin in the universe, determinism and free will. If your actions are predestined by these loops, do you truly have free will? The Predestination Paradox suggests that all events are fixed. You were always destined to invent the time machine, and your journey back in time was inevitable. This raises unsettling implications. If everything is predetermined, are our choices meaningful? Or is free will an illusion in a universe where the past, present, and future are already set in stone? The Autoinfanticide Paradox. What if, in a moment of doubt, you choose not to save your younger self? The Autoinfanticide Paradox posits that you cannot prevent your own death once the event is part of the fixed timeline. The universe seems to forbid such self-destructive interference with its established history, making genuine free will in time travel seem impossible. The physics of time travel. What does science say? Despite these paradoxes, modern physics provides compelling evidence that traveling to the future is not only possible but an inherent feature of our universe. Traveling to the past, however, remains speculative and riddled with theoretical and practical hurdles. Relativity and the nature of time. Albert Einstein's groundbreaking theories revolutionized our understanding. Special relativity, 1905, demonstrates that time is relative, depending on how fast an observer moves. Traveling near the speed of light causes time dilation. Time slows down for the traveler relative to stationary observers. This phenomenon has been experimentally confirmed with atomic clocks on airplanes and satellites. GPS systems, for example, adjust for these relativistic effects to maintain accuracy. General relativity, 1915, unites space and time into a fabric called spacetime. Massive objects curve spacetime, creating gravity. This curvature affects how time flows. Closer to massive objects, time runs slower. Black holes, neutron stars, and gravitational waves are all manifestations of spacetime's dynamic nature. Testing and confirming spacetime's curvature. One of Einstein's key insights was that massive objects cause spacetime to curve, producing what we perceive as gravity. This prediction was spectacularly confirmed during a 1919 solar eclipse, when starlight bending around the sun matched Einstein's calculations. Since then, Phenomena like black holes and gravitational waves have continually supported the idea that space-time is a dynamic, malleable fabric. Time travel to the future, scientific certainty. If the past is fixed within the block universe, is traveling forward in time possible? The answer is yes. Time dilation, verified through experiments and technologies like GPS, confirms that moving at high velocities or residing in strong gravitational fields causes clocks to tick more slowly relative to others. For example, astronauts aboard the International Space Station age slightly less than people on Earth because of their velocity and the weaker gravity they experience, an everyday form of forward time travel. Cosmic rays and muons. In the 1960s, physicist Bruno Rossi used cosmic rays to demonstrate relativistic time dilation. Muons, unstable particles generated high in Earth's atmosphere, travel at nearly the speed of light. Despite their fleeting half-life, many reach the Earth's surface, thanks to time dilation slowing their decay from their perspective. This natural phenomenon provides compelling evidence that moving at relativistic speeds effectively allows us to travel into the future. Potential for human time travel. Theoretically, accelerating humans close to light speed could enable significant time travel into the future. However, the energy required grows exponentially as speeds approach that of light due to Einstein's E equals mc squared. The mass increases, demanding astronomical amounts of energy, far beyond current technological capabilities. Even so, the principle remains valid. Moving near light speeds results in less elapsed time for travelers compared to those remaining stationary. Black holes and gravity wells. Another method involves strong gravitational fields. Think black holes or neutron stars. Clocks operating near these objects run slower than clocks far away from them. If humans could survive near a supermassive black hole, they could effectively jump forward in time relative to the rest of the universe. This concept has been popularized in science fiction and explored in movies like Interstellar. The challenges of traveling backward in time. While forward time travel is supported by physics, backward travel faces formidable barriers. Wormholes, hypothetical tunnels in space-time, could connect distant points or different times. If stabilized, they might allow travel to the past. However, maintaining a wormhole requires exotic matter with negative energy, a substance not yet observed or understood fully. Tipler cylinders and cosmic strings, massive rotating cylinders or defects in space-time could, in theory, create closed time-like curves, paths that loop back in time. Yet these require conditions that are physically unattainable, such as infinite length or immense rotation rates. Quantum mechanics and negative energy, quantum effects like virtual particles, produce tiny regions of negative energy that might stabilize wormholes momentarily. But scaling this to macroscopic, human-sized time machines remains speculative. Resolving the paradoxes. The most famous time travel paradox is the grandfather paradox. If you travel back and prevent your grandfather from having children, how could you exist in the first place? Several theories aim to resolve this. Novikov's self-consistency principle suggests that events in the past are fixed. You can't alter history in a way that creates contradictions. Any attempt to change the past fails because the universe prevents paradoxical actions. Many worlds interpretation, MWI, of quantum mechanics offers an alternative. Every possible outcome occurs in a branching multiverse. Traveling back in time would create a new, separate timeline where your actions don't affect your original history. This way, killing your grandfather in one universe wouldn't erase your existence in your original timeline. Quantum mechanics and the branching multiverse. According to Hugh Everett's MWI, each measurement or event splits the universe into multiple copies, each realizing a different outcome. If you go back in time and change something, you're not altering your original timeline, but creating a new branch. This interpretation circumvents paradoxes and suggests that backward time travel might be theoretically possible, but only by entering a different branch of reality. The future of time travel, possibilities and limitations. While the concept of traveling into the future is scientifically validated and practically achievable in principle, backward time travel remains speculative and fraught with challenges. Theoretical constructs like wormholes and cosmic strings offer tantalizing possibilities, but no experimental evidence exists for their existence or stability. Moreover, the paradoxes and causality issues pose profound philosophical questions. Does the universe enforce a strict causal order, preventing paradoxes, or do alternate timelines and multiverses provide a loophole? In conclusion, our universe, as described by Einstein's relativity, is a four-dimensional space-time where past, present, and future coexist in a vast, unchanging block. Time travel into the future is supported by experiments and observable phenomena, while backward travel remains a tantalizing puzzle, one that challenges our notions of causality, free will, and the very nature of reality. As scientific understanding deepens and new discoveries unfold, perhaps one day we will unlock the secrets of temporal navigation. Until then, we can marvel at the universe's complexities, appreciating that the past is not lost but woven into the fabric of space-time, waiting for us to explore.